Okay, so now we get the idea of what the extreme value theorem is about and kind of how it works with the graphs. That as long as we have a function that is continuous on a closed interval, then we're guaranteed that there must exist a global max and a global min. So now what we're going to do is we're going to look at what if we don't know what the graph looks like, but what we have is the algebraic representation of the function. We have the formula. How can we use the extreme value function in order to find these global maxes and global mins that we are guaranteed that there must exist? So first off, let's think about at what different values can the extreme values occur. And remember, we're only going to be talking about a continuous function on a closed interval. All right. So the first case is if we have an x value for which we have a horizontal tangent line where the derivative switches signs. So if we're thinking about what the picture of the graph would look like, whether it's a max or a min, the derivative, okay, the tangent line slope, the derivative is positive, 0, and then negative here. So at the point where we have a 0 horizontal tangent line, 0 slope horizontal tangent line, and it switches sign, that would be from plus to minus would be a max. And then over here, where we have a horizontal tangent line, and now we're switching from a negative slope to 0 to a positive slope, and that would be a minimum. So that obviously would be a value that we're going to worry about where there might be a global max or a min. Now, there could also, however, be a global max or a global min at a cusp, because if it's a cusp where you are switching signs, coming across here, positive slope does not exist, no slope to negative slope. And then here's negative slope, d and e, and then positive slope, that it could be possible that if you have a cusp, that would be a value of an extrema. The reason why I'm focusing on the switching signs part is that if you had a cusp that came in and then did this, this would not be considered an extrema because there are points higher to it over here on the right side and points lower on the left. So it would have to actually have a derivative or a slope that would switch signs before and after. Right? So that's number 2. We also are looking at the endpoint of a closed interval as well, because we saw earlier that sometimes the global extrema happens at the endpoints. All right. So if we have the equation of a function, we just don't have a picture. The extreme value theorem doesn't really say here's how you find it, but we are going to use the extreme value theorem in order to find it. Okay, so now we kind of have this idea about where these extreme values can occur. We're going to define what's called a critical value. And a critical value, first off, it has to be in the domain. This is one of those things that gets kind of sidelined and forgotten as we get deeper into this chapter, that we first have to have a value in the domain. So there's no jumps, holes, infinite discontinuities, things going on. So that either the derivative is 0 or the derivative does not exist, so that's the cusp part. So this is the horizontal tangents or the cusp. It could even have vertical tangents, provided that the vertical tangent is also kind of a cusp, kind of this idea. So we'll, in general, just say the derivative does not exist. And at these critical values, where the derivative is 0 and the derivative does not exist, that's what we're going to call a critical point. A critical point is a point where there may be an extrema. So we're going to check it. So we're going to first find the derivative, figure out where the derivative is 0 or doesn't exist, and we're going to call that a critical point, and that's going to be a point that we're going to check to see if that's an extrema. Okay? And basically what we're going to add, this doesn't have a name to it, but we're basically going to use EVT, that the idea is that your absolute or global extrema can only occur at a critical value or the endpoint of an interval. And this is again assuming EVT applies. Assuming EVT applies. Okay. So before we set out to find them analytically, let's address and kind of do the definition of the other type of extrema, which are called local extrema, which is the idea that if you have an open interval containing C, so for like if I go to this picture right here, even if my function continues, let's put some axes on here, if I can pick an open interval, say we'll go A to B. So if I could pick an open interval from A to B, and if immediately to the left of some C value in between, so obviously in this picture my C value would be right here. So for some C that is in this open interval, okay, that if I look immediately to the left and immediately to the right, if there are no y values larger than the y value for C, then f of C, then it's a local min. Okay, a fancy way of saying what you already know. And if there are no y values smaller, then it is a relative or local min. One point to make about these local maxes and mins is that they cannot occur at endpoints. Okay, they must be occurring at actual values in it. Like if I have the interval, because it's going to be an open interval, so we're assuming that that's kind of not included when we look at this picture of the graph, that this is where we're kind of zooming in on. And we're looking for a point on the graph for which there's none higher, and an endpoint is not going to be considered possible for a local extrema. Okay. And so that's just a definition, pretty straightforward. And then again, this is that second note that they cannot occur at the endpoint of the interval. Okay, there are some gray areas with that. There are some textbooks that may consider the endpoint to be local as well as maybe a global one, but in AP Calculus world, the endpoints cannot be local extrema. They can only be global extrema. All right. And also notice that the theorem doesn't say that there is a relative or local extreme value at every critical value. It just says that there may be. And the fact that there's potential, prospective, or possible location, that just means it's critical, that we need to check it. That's why it's critical. Right? So here we're identifying all the critical values of the graph. And then we're going to determine whether the critical value actually is a max, a min, or neither when you're looking at it. All right, so in this picture, our critical values, we would have a critical value here at B because we have a horizontal slope. We would have a critical value at D because of a horizontal slope, and a critical value at E. So critical values, x equal to B, D, and E, because f prime of these values, f prime of x equals 0 for these values. Okay, then we also have the critical values that are going to occur here at C as well, x equal to C, and that's because your derivative, f prime of x, does not exist for this value. Okay, so those are my critical points. And then of the critical points, the ones that are local extrema, we would have, again, I labeled this earlier, a local max value here and here. And we would have local min values here and here. All right, now this next example is this idea that you don't always have to have relative extrema. They don't always have to be at nice, tidy hills and valleys, and it has to have a continuous function. So here's an example of where we're looking at, suppose we had this graph, and let's take a look at our critical values here. Let's do our f prime of x equal to 0, all the values for that. So let's label it critical values where f prime of x equals 0. So as we scan through here, right here, all of these points in this interval would have a slope of 0, right? Because you're on a constant horizontal line. So for all x in the interval from -1 to 1, would be a place that would be considered critical because they have a slope of 0, and they would be candidates for local maxes and local mins. And in fact, they are local maxes and local mins. That would be the only place where we have the derivative equal to 0, and then we have the derivative does not exist. Okay, the first place, and we're doing -4 to 4, so we don't consider the endpoints, okay, because that cannot be a candidate for these. We do consider here at -3, because you have a point discontinuity, the derivative would not exist. We would have at -1, we have a jump discontinuity at 1 and at 2. So at all of these places, we have discontinuities that are not endpoints, for which we have critical values. Now, in terms of our extrema, again, going through and classifying, right here for these, we would have a global max and min of 2 at x element of this -1 to 1, not including the endpoints. And then we would look at each of these, and we would look at, say, here at -3. And now it's a critical value. Now we're going to pick an open interval kind of close to -3, and then I'm going to look at the y values at -3, and I'm going to look at the y value to the left and to the right of that. Okay? And if I look to the y value to the left and the right of that, they're always lower than the y value at -3. So that would be a global max. There are none higher in an open interval that I select around this. And it's any open interval. If I can get any open interval for which there are none higher, then that's a global max. So we have a global max of 1 at x equal to -3. Okay. And then we're going to take a look at -1. Now at -1, this is going to be a neither, because if I pick an open interval around -1, no matter how close I get to -1, there will always be y values lower than the y value at x equal to -1 and y values higher than the y value at x equal to -1 on the left and on the right. So that is actually not a global max nor a global min. Okay, over here at 1, another critical value, or like what's happening here at 1, the y value for 1, if I pick an open interval around 1 and look at the y values, compare them to the y values of 1, the y values over here on the right hand side are higher. The y values over here on the left-hand side are higher, so therefore there are none lower than the y value here at 1. So there is a global min of -1 that occurs at x equal to 1. And I just notice I'm making a mistake here because we're not doing global, we're doing local in this little selection. So let me go back and fix that. The global comes from the absolute highest and lowest. Let's do local. We'll talk about global in a second. Local and local. All right, and then my other critical value here was 2. And so at 2, we can look up here, we do our open interval on either side, and we look at the y value at 2, and then we compare the y values immediately to the left and to the right of it. Now remember, we're talking a little tiny, any interval, if I look immediately to the left and immediately to the right, they're all above. So I can select an open interval for which there are none lower than this point. Yes, it is true that if I go out wide enough, there will be some that are lower, but the idea about local means if you can pick any open interval around 2 for which there are none lower, then it's considered a local min. And I can just squeeze my interval in and make sure that the y values I'm comparing are up here. So there is a local min of, I don't know what it is and I don't want to guess, and so this is, oh, we're doing h of x. See, it's nice that I actually read the problem when I come in here and then realize I'm naming things. So h prime, So local min of h of 2 at x equal to 2, since I don't really know what that is. Okay, and then remember that endpoints are not candidates for critical values and then local mins. Now notice I didn't say this also, is that kind of understood here is that you can't be a critical value unless you actually are in the domain of h of x. And even though, just kind of let's talk about the domain of h of x while I'm here, the domain, even though there's a lot of point discontinuity and a jump discontinuity here and here, that everywhere there was a discontinuity, it actually is defined and has a y value. So the domain is -4 to 4. So all of these were candidates for critical values. If this point had not been there, if I were to take this out, and if the domain had been -4 to 1 and then 1 to 4, 1 would not have been a candidate for a critical value because it did not actually exist on the original function. So that's, like I said, that's one of those things that kind of gets forgotten as we get into this. We're so worried about checking the derivative being 0 or doesn't exist that we forget that technically we should first check that the domain, they exist in the domain. All right, so we've done that and we have our local maxes and mins. Now, just because we're interesting and we're here, let's talk about our global max and min on the closed interval of -4 to 4. Now, we're not guaranteed to have a global max and a global min, but we may. So if we look through these, up here, this would be our highest y values up here. There are none higher. So I would say that we have a global max of 2 at x, an element of -1 to 1. Okay, and then we scan across for the y value for which there are none lower. Over here at this endpoint, there is a global min of -2 at x equal to -4. So even though we're not guaranteed to have them, we actually did at that place. And again, just make one more note to yourself. Just remember, because we always forget this as well, endpoints cannot be critical values or local extrema. However, they can be global extrema. Okay? All right, so we get that down, and now let's come over here to our next example. So the first skill is basically figuring out the critical values of functions, and we're given the algebraic. Now, a couple of things to think about as we're doing this. We should, as always, think about domain before we start. This is a polynomial, so domain is -infinity to infinity. So pretty much any value where the derivative is 0 or does not exist is going to be our critical values. Now we also know, because this is polynomial, kind of leading into this, that f of x is continuous for -infinity to infinity. So pretty much the only critical values are going to occur when our f prime of x is equal to 0 in this case. So we're using some prior knowledge as we're doing this. So basically what we're going to do, we're just going to take the derivative. So f prime of x, so step 1 in finding critical values is to find f prime of x. So we multiply, so we would get 4 times a half, so 2x cubed minus 3x squared minus 2x minus 0. And then because we want to set this equal to 0, we might want to put it in a nicer form. So let's factor, let's remove a GCF, 2x squared minus 3x minus 2. And let's see if this factors a little bit farther. Let's see, we have a 2x and an x and a 2 and a 1, and let's do minus and plus. So with our derivative equal to there, and this is where you got to be very careful about your notation and your linkage, that we would say f prime of x equals 0 when x equals 0, x equals -1/2, and x equals 2. So my critical values are going to be when the derivative equals 0. I do not have to worry about the derivative not existing because polynomials are, I guess I should also add up here, their domain is everything, so we don't have to worry about any non-existence. The function is continuous, and we also know that it is differentiable, hence smooth, so that I don't have any vertical tangents and I will not have any cusp involved in this one, so I don't have to check for that. Alright, so now let's come over here. We have an absolute value. Let's kind of do our, hey, cusp alert. Anytime you have absolute value, that's going to be our piecewise. We might want to remind ourselves, since we're going to be taking a derivative, we did this in an earlier section, but the derivative of the absolute value of x is x over absolute value of x. And then also if I was doing chain rule, kind of as a side on this, the derivative of the absolute value of u with respect to x, let me slide that over there, is going to equal u over absolute value of u times u prime. I will leave this to you to kind of work your way through, but we did this in an earlier video. So we're going to take the derivative. I do have this idea that there's a cusp. Let's talk about domain. This is really an absolute value graph that has been shifted to the right 4, flipped, and then moved up 2. So from prior knowledge, we know our domain is negative infinity to infinity. We also know that g is continuous, but not differentiable everywhere, and that's because we have this whole cusp alert. So we are going to be taking a look at, we need to know when our derivative is 0, and we're going to need to know when our derivative is going to be d and e. So we're going to check both f prime of x equal to 0 and d and e for our critical values. Alright, so let's take our derivative. So g prime of x, derivative of a constant is a constant. Let's just bring the negative down. Now I have the absolute value of u. So the derivative of the absolute value of u would be u over absolute value of u times the derivative of u, which was x minus 4, which is just 1. Okay, so we're pretty much ending up with negative times this x minus 4 over absolute value of x minus 4. So now we're going to look at when does the derivative not exist. I like to do doesn't exist first. So g prime of x does not exist when you have a division by 0 problem. And so that would be does not exist when x equals 4. Now 4 was in the domain, because you want to check that, it was in the domain, so that's where we're going to be looking for. It was in the domain, it was continuous, we're looking for a cusp or a vertical tangent in this case. It could also be this piecewise, so we do want to take a look at this and see what's happening. Later on we'll talk more about graphs and how do we do curve sketching given these pieces of information that we find. Right now we're just trying to find critical values. Now in terms of g prime of x equal to 0 equals 0, that would be never in this case, so you have no critical values from that, because the only part of a fraction that equals 0 would be the top, and 4 makes the top 0, but it also makes the bottom 0. So this actually has a jump discontinuity on the derivative because of the piecewise. So d and e always wins. It's already a discontinuity, so you can't be a 0. So the only critical value here is 4. All right, so let's take a look at our next one. All right, and I'll tell you here that when you have a odd root in here, this is going to be a cusp or vertical tangent alert. Anytime that you see odd roots involved, like if you remember when we did x to the 1/3, that had a vertical tangent. Here we have x to the 3/5, and so I'm going to worry a little bit about a vertical tangent on this one, possible cusp. All right, so let's talk about our domain, just to kind of always something we should do first. Our domain here, this is odd roots, that's always defined, and times a linear, so our domain is everything's going to work, no problems there. Is it continuous? I believe so. We don't have any square root of x squared or anything that might cause us to have a piecewise, so it's continuous. We're not so sure about the smooth part. So some of this that maybe I know for easier functions, maybe I don't know for this one. But we're going to use the derivative to help us determine really what's going on. So we're actually going to check both f prime of x equal to 0 and d and e. And as always, I always forget what letter I'm using, so I'm going to come back and fix that to be g prime of x. Always important. Alright, so we're going to take the derivative. Now, you have options here. We could use the product rule, or we could simply just multiply this out and make it into a polynomial, which I'm going to do. I think that's easier. So 4x to the 3/5 minus, remember we're adding, so it would be x to the 8/5 after I multiply. So my derivative, f prime of x, is going to equal 3/5 times 4, so 12/5 x to the subtract 1, negative 2/5 minus, let's see if I can squeeze this in here, probably not, 8/5, and imagine with me x to the 3/5. Now I'm going to do a little work on this because we have to get this in a nicer form because it really helps to have it as a single fraction. This is really going to be 12 over 5x. Oh, actually, you know what? Let's not do that. Let's do factoring out the GCF because we definitely have a GCF here. So I would say that this was 8/5 and 12/5. So I would go with, I can pull out a 4/5 x and to the smaller power, so negative 2/5. So we're going to pull that out. Now what we want to do is, I'm going to actually cheat. I'm going to make myself have some more room so y'all can see what I'm doing. Okay, due to the magic of I can shrink here, I have a little bit more room, so I rewrote this. So I'm pulling out 4/5 x to the negative 2/5. So when I pull the 4/5 out here, I'm left with a 3. And then over here, I'm pulling a 4/5 out, so I'm left with a 2x, and then we're subtracting, so 3 minus negative 2/5 will be 3 plus 2/5, or 5/5, or 1. And so what we really end up with, our nice form of our derivative, would be 3 minus 2x over 5, and then I like to go at this point the 5th root of x squared because I think that's a little easier. So that's what we mean by we're going to find critical values. This is what I call a nicer form. Alright, so now I'm ready to do my critical values, and I like to do the d and e first. So f prime of x, we are named f, right? So f prime of x d and e when x is equal to 0, because we have a division by 0 problem, and then f prime of x equals 0 when the top is 0, and so that would be when x equals 3/2. So we have two places where we're going to have our critical values. All right? And so later on we'll figure out, well, what really is happening at those places. Is it an extrema? Is there a cusp? Is there a vertical tangent? What's going on? Alright, so here's going to be our closed interval method for finding extrema. So this is how we're going to use EVT to find global extrema. I know we've been talking about local for these critical values, but the only reason we've been talking about local is because your global extrema are either going to occur at endpoints, which is why we're going to first identify our endpoints. We're going to make sure our function is continuous and that we have a closed interval, so EVT applies. EVT applies. You do that first. Then you identify your endpoints. Number 2, your global extrema could occur at critical values. So we are going to find the critical values. We want to verify that they're in the domain, okay? And they have to be in the specified interval, because otherwise they don't even have any bearing on the problem. So you do want to make sure. I am going to kind of circle this in red, because these are two things that you have to remember to do. And then basically all you have to do is find the function values. We're just going to make a little chart where we go x and then f of x. You're going to do your endpoints here, and then you're going to do your critical values, however many you have, and just find the y values, whatever they are. Okay? So we would have f of a, find f of b, find f of c using your formula, find f of this endpoint, and f of, we'll say endpoint 1 and endpoint 2. So you just plug them in and you make a list. You always just organize it in a chart. That's the easiest thing. And because we are guaranteed by EVT to have a global max and a global min, the largest will always be the max and the smallest will always be the min. So you just scan through here and look for the largest and the smallest. Alright, and so I know this is like a joke, but it's basically like trying to be on a hit game show, like Jeopardy, we'll call it Extrema. So pretty much you know that whoever has the biggest value is the winner, so winner, global max. Whoever has the lowest value is the loser, the global min, and the in-between person was just a critical point or an endpoint that just didn't win the game. So the absolute minimum, or absolute maximum, would be the 40 to 20 located at x equal to c, if I label these as points A, B, and C. The absolute minimum would be 20 to 20 at x equal to b, and the green ribbon for participating is x equal to a, because the 3120 was neither a max or a min. So EVT is actually one of the easiest ones to do, as long as you realize that you will get to use EVT. So what you're going to do is you're going to go, hey, I want to find the extrema, and usually when we say that we mean the global extrema of this function on this interval. So the first thing that you should notice is you go ding ding ding, I have a closed interval. I am looking for global extrema, and then I go, hey, is that function continuous? And the answer is yes. So f of x is continuous on a closed interval, so EVT applies. So that's your first thing. Now remember, we're in chapter 4. This is only the first section, so you're going to have several theorems that are going to work, and you have to pick which one applies. So this is stage 1. We only have one theorem so far. Hey, EVT is going to be the correct method to use for this. So you figure that out first. Then you go, okay, now I'm going to figure out once I know EVT applies, I actually start a little chart over here because I know I'm going to use it, and I add my endpoints in on my chart. I do that first because I know I'm going to need them. You might as well plug them in and calculate your f of 1 and your f of 2 at this point, because you know you're going to need to check them. So I'm like, hey, it's EVT. I'm going to do my endpoints. F of negative 1 should give us 15, and f of 2 gives me negative 48. I'll leave that for you to verify. So I figure out that we have a continuous function on a closed interval. I'm using EVT, so I immediately do my left endpoint, and then I do my right endpoint. Then I come along and I go, all right, the only other place where I might have global extrema would be at my critical values. And again, I am going to use prior knowledge, and I'm going to be like, this is a polynomial. F has a domain of negative infinity to infinity. It's continuous and smooth. So at that point, I know I'm pretty much looking for f prime of x equal to 0. Okay. So then we just do the work for that. We show this is all nice work that you're going to show for this problem. You show finding your derivative. So we'll multiply. We'll get our 12x cubed minus 36x squared. Then we're going to set f prime of x equal to 0. Maybe before I do that, maybe I want to factor. I can pull out a 12x squared, and that's going to leave me with x minus 3. So once you have it in a nice form right here, you're like, well, f prime of x equals 0 when x equals 0 and x equals 3. Now we've already determined in the domain, both of these are in the domain. Now I'm going to determine, are they in the interval? What you will notice here is that the 3, while it's a place where you have a horizontal tangent, this is not in the interval, so I'm removing it from my consideration because I'm only trying to find global maxes on the interval. The one that is in the interval, 0, I add that to my chart. I calculate f of 0, which is 0. Right? And now we're ready to answer the question. This is how easy this is. We look at our chart and we say, what's the largest? Here's the largest, so that's my global max. I look for the smallest, that's my smallest, so that's the global min. So we would answer the question and we would say the global max value of 15 occurs at x equal to -1, and your global min value of -48 occurs at x equal to 2, and x equal to 0, while a critical point, just gets the participation by getting included in the list, but it's not a global extrema. See, I mean, this is so straightforward. All you have to do is EVT applies, make sure you know your domain, find your critical values, make sure they're in the interval, and then calculate, and then we're done with that one. All right. Let's go to here. Again, we're trying to find the global extrema of this. We have a cusp vertical tangent alert here because I have an odd root, and here's my interval. So, global extrema is what I'm looking for. I have a closed interval, check, and then is this function going to be continuous? And it's an odd root function, which we know is continuous. X to the 1/3 is continuous. All odd root functions are continuous, so we're going to be okay with that. It's not polynomial, so don't say because it's polynomial, but we do know that it is continuous. If we had to, we probably should kind of basically do our reason why, because we always had to have reasons if this was a free response. So we might be like f of x is continuous. Let's see if we can scan our knowledge about continuous functions. We know 2x is linear, and that's continuous. We know that 3x to the 2/3 is a continuous function because it's an odd root. Okay, all odd roots are continuous, all linear functions are continuous. The sum of continuous functions is continuous because it's a combination of continuous functions. Please do not say polynomial. So we've got continuity. We have a closed interval. Check. So I know EVT applies. Okay. So now we're ready to start our method. Here's my x and f of x. I add my endpoints in. I just like to leave a space in the middle. I can fill in my chart. So we do f of -8 and f of 1. F of -8 is -28. I'll leave you to verify. F of 1 is -1. And again, I'll leave you to verify. So that's our start. We know that EVT applies, so I start making my chart so I can check and see who wins the race. Then I come over here and I'm going to find my critical values. We might have a vertical tangent alert. So I am going to check when the derivative is equal to 0, and I'm going to check when it does not exist. So I'm going to check both of those. So we first find our derivative. So we would have 2 minus 2x to the -1/3. And again, we like it to be in a single fraction, so I'm going to go ahead and rewrite this as 2 minus 2 over x to the 1/3. We might add a form of 1 in here, kind of working ahead. So we get 2x to the 1/3 minus 2 over x to the 1/3. Right? So I'm going to do my f prime of x. I like to separate them. Let's do d and e first. We look to the bottom. So that's when x is equal to 0. Is 0 in my interval? Yes. So I add that over here. F prime of x equals 0 when the top equals 0. So 2x to the 1/3 minus 2. When x to the 1/3 equals 1, this is cube root of x. So x equal to 1, just cube both sides. And is that in the interval? Well, yeah, it's one of the endpoints, so I don't need to list it again. It's already there. We plug in 0. F of 0 is 0. And then we scan through. We've got our list. Our endpoints are critical values. The lowest, that's my global min. And the highest, that's my global max. So we would basically state that we have a global min of negative 28 at x equal to negative 8. And we have a global max of 0 at x equal to 0. And then we're done with that problem. All right, we're going to do one more example and then kind of finish up this video, and I'm going to save example 12 by itself because that one takes a while. Again, we're going to determine if EVT applies. We have two trig functions which are continuous being combined, so f is continuous because trig functions sine and cosine are continuous. I have a closed interval, so 0 to 3 pi over 2, so check, so EVT applies. And again, I'm stressing that you need to check this because remember, we're in the first section. There will be several more options of what to do if EVT doesn't apply. So that's why we check that. If given a chance, and if EVT applies, you want to use EVT. If it doesn't apply, then you have to go find another way to answer the question. So we're checking to see if the easy one works, which is EVT. Once we know that, we're going to do my chart, x, f of x, and put your endpoints, 0, 3 pi over 2. Calculate f of 0. Now this does require some sign, knowing some trig. The sine of 0 is 0. The cosine of 0 is 1, so I end up with 0 minus 1 or negative 1. And then we have 3 pi over 2. The sine of 3 pi over 2 is negative 1. And then the cosine of 3 pi over 2 times 2 would be the cosine of 3 pi, and the cosine of 3 pi is negative 1, so it ends up being negative 1 plus 1. Oops. Sorry, it would be helpful if I multiplied by 2, and so that gives me negative 1 down here. All right, so now we're going to come over and we're going to find our critical values. Oh, and I didn't check, and I should be going negative infinity to infinity is the domain, so they are definitely in the domain. And same thing up here in example 10, if I didn't check, the domain was negative infinity to infinity, so they were in the domain. See, that's the first thing you forget, to check and make sure that it's in the domain. All right, so my critical values, let's do our find our derivative, f prime of x. Derivative of sine is cosine, so 2 cosine of x. The derivative of cosine is negative sine, u, don't forget chain rule, times du. So we put that in, and we're going to set it equal to 0. Let's do that first. All right. So I need to solve this. Oh, such a sad thing. How do I solve that? How do I solve 2 cosine of x plus 2 sine of 2x equal to 0? We might need to remember an identity. Sine of 2x is 2 sine of x cosine of x. So times 2 plus 2 cosine of x. So I make an identity substitution. Why did that help me? Because now I have a common factor that I can pull out. I'm going to pull out a 2 cosine x. I'm left with 1 plus 2 sine x equal to 0. And so I can do 2 cosine of x equals 0, and that happens at x equal to pi over 2 plus pi k, every y-axis quadrantal. And then we have sine of x would equal negative 1/2, subtract 1, divide by 2. Sine of x equals negative 1/2. If you are in quadrant 3, that would be at 7 pi over 6 plus 2 pi k, and x equals 11 pi over 6 plus 2 pi k. But now remember, we have to get these in the interval that we're looking at, and we're doing 0 to 3 pi over 2. So in the interval from over here, pi over 2 is definitely in, so I add that. 3 pi over 2 is this endpoint, so, and then would be out in either way. So that's all I get from that one. Now from over here, we would have 7 pi over 6. The next one would be out, and 11 pi over 6 is not in the interval. So of our critical values, we check and make sure that they're in the interval, so we add them to our list. Now I go back in and I do my plug and chug. I do f of pi over 2, okay, which is going to give me 2 plus 1 or 3. And then we do f of 7 pi over 6. And again, I'm leaving you the trig to remind yourself what the trig is. All right, so we end up with negative 1 minus 1/2, which equals negative 3/2. And then we scan through our problem. The largest is 3, so there's my global max. And the, smallest, so we have negative 1, negative 1, negative 1.5. So negative 1.5 wins our global min. Stop that. Global min. So we would say we have a global max value of 3 at x equal to pi over 2. And we have a global min value of of negative 3/2 at x equal to 7 pi over 6. And then we're done with that problem. So that's the idea here, is that this is our first of many theorems about identifying special features of graphs, of which global maxes and mins are one of them. And whenever possible, if we can use EVT, that is always your go-to. If you have a continuous function on a closed interval and you are being asked to find global extrema, EVT is always the theorem that guarantees that you have them and pretty much gets us to the point that it has to either be at an endpoint or a critical value. So here's our technique for finding them.